weak structures and p-stacks. This presentation is almost entirely based, as you can read on the paper by Mr. Guldurdek from Turkey that was published in 2012. Basically, it is based on the notion of weak structures, and the notion as such was introduced several years earlier by Chasser, who is responsible for the term generalized topologies too. And then weak structures were studied by many authors all around the world. In particular, you can find both soft and binary soft weak versions of the concept. Just look to the bibliography of our video. Well, if we have some subfamily of subsets of certain non-empty universe X, then we say that this family, namely W, is a weak structure in X if and only if we have a guarantee that empty set is somewhere among those distinguished sets. So the notion is very general, much more general than the idea of topology or supra or infra topology, or even more general than the idea of minimal structure. Clearly, the elements of W are W open sets, while their complements are W closed. The union of all W open sets contained in A is W interior, while the intersection is W closure. Here there are some basic properties of both operators, like for example that interior is contained in the initial set, which is contained in its closure, like this monotonicity here, and those properties that are very well known from topological spaces, and they hold in these weak structures too. This theorem is also known from topological spaces, that some point X belongs to the interior of A if and only if there is some open set V contained in A such that X belongs to V. Analogously, we have a characterization of closure, which is visible here, that we are in closure of A if and only if we are in every set V that is open. If every set V that is open and contains our element X has non-empty intersection with A. Okay? These properties are specific in the sense that their converses are true in topological spaces, but not necessarily in weak structures, as you can see here. If our set is open, then it's identical with its interior. If our set is closed, then it's identical with its closure. The notion of neighborhood, not necessarily open neighborhood, because the assumption is that we say that V is a neighborhood of X if there exists a W open set U such that X is in U and U is contained in V, and then we can define the set of all neighborhoods of X. The notion of p-stack, a collection F of subsets of X, is called a p-stack if it's closed under supersets, as it's written here. And moreover, for any two elements in F, their intersection is non-empty. So the family of all the neighborhoods of X is non-empty, if it's non-empty, because in weak structures it can be empty, but if it's non-empty, then it satisfies the properties of p-stack, which is written here, so we call it weak neighborhood p-stack at X. We say that our p-stack converges to X if and only if the whole family of neighborhoods of X is contained in F. If this family is empty, if there are no neighborhoods, then we assume that any p-stack converges to this particular X. There are three new symbols introduced by Guldurdek. First, the collection of all p-stacks on X, then .x, the collection of all those sets in X that contain X, so in some sense supersets of the element X, And this symbol, which is rather specific because we have something like intersection of two p stacks, but it's defined in terms of well, all the possible unions of f and g, where f is in this Gothic p stack, f and g is in this Gothic p stack g. So the third definition is surprising, at least at first glance, because here we have unions, but it's denoted with intersection here. The author proves the following theorem, that x dot converges to x for all elements. If some p stack converges to x and this p stack is contained in another p stack, then this external superset p stack also converges to x. And if two p stacks converge to x, then the one defined in this manner converges to x2. We omit the proof, but it's rather simple. You should check in the original paper. Moreover, we have two new operators, capital I, one could say capital interior, the set of all those elements of A such that A is their weak neighborhood, and closure, as you can see, the set of all those elements of A such that they have non-empty intersection with every neighborhood. But the author proves that they collapse to the initial notions of interior and closure, which is written here. And then we have the following theorem: if x belongs to this capital interior, so as we already know, it means that if it belongs to the interior as such, this is identical with the following fact, that for every p stack that converges to small x, we have that A is an element of this p stack. And analogously with closure, if there exists x belongs to this capital closure, if there exists a p stack h such that h converges to x, and for every h in Gothic h in our p stack, and the intersection of h and a is non-empty. Well, rather simple proofs. So these were only those initial terms, but then the very core of the paper that will be discussed in the next video, I hope that it will be today or tomorrow, we will see, is about separation axioms. There are several separation axioms, T0, T1, regularity, T4, that are analyzed in the context of p stacks. The proofs are slightly more complicated, more interesting. So you will see, or you can just check the original paper of Guldurdek. It should be umlaut U, sorry for the author, weak structures and p stacks. The original paper of Chasser about weak structures, which was published in Acta Mathematica Hungarica, here. Then we have two other papers mentioned. One is about soft weak structures, and one about soft weak structures but in binary setting. Maybe you remember that there are so-called binary topological spaces, so this is their generalization. Thank you very much for your attention. Goodbye.